Hey everyone, today's topic we're going to be looking at is regression analysis. This is one of the topics that is definitely not going to connect to the others we've looked at so far. It's a bit of a bummer that we're looking at it now versus how I'd originally planned at the end of this semester, because there's a couple of functions we haven't talked about in detail yet, but we'll do our best here. So before we get started, regression analysis I think is something we've been introduced to before, not in this course, but you've probably seen before. Let me just build this a little bit. So let's pretend that I was going to collect data on students in this classroom, and I wanted to graph that data. And let's say that the data I was collecting was about the height and shoe size. So let's put shoe size over here, and let's put height over here. And let's just say that heights are increasing, shoe sizes are increasing. What's going to happen? If I went through and collected, let's say from 10 males, I collected heights and shoe sizes. What's going to happen is the taller you get, probably the bigger your foot is going to be. It's 3, 4, 5, 6, 7, 8, 9, 10. And then maybe we get some data that looks like that. So if we were to plot the data, we'd get some scatter plot. And they might not make, an exact line here, but they would sort of trend upward, where again, the taller you are, the bigger your foot's going to be, or the shorter you are, the smaller your foot's going to be. And what we could do, the process like this, is sort of estimate the relationship between the points by creating what we call a line of best fit. And I'm sure that's something that you've talked about before. So if I was to make a line of best fit for this data, maybe it looks something like this, where it sort of represents, it hits some of the points and you got some above and some below. So this might be an estimated line of best fit for this situation. Now, the purpose of being able to calculate a line of best fit for this scenario would be to make some predictions for values that we don't know. So let's say that the tallest person that I collected data for here, let's just say that that person was like 6'2", okay? And then I know data for someone who is 6'2", I could approximate for my data what their shoe size is going to be, but maybe I want to know what's the shoe size for someone who's 7 feet tall. Well, I don't have data for that. Now, even though the data stops, the line is going to continue forever, so I could use my line to say, or to go out to 7 feet tall and say, oh, that person's going to have a shoe size that is, whatever it happens to be. So we collect some data. Based on the data, we look for a relationship, and then we calculate a line of best fit if the data is linear. It's possible that we collect data and it doesn't look like a line. Maybe the data makes more of a U shape, in which case we could calculate a parabola of best fit. Or maybe the data doesn't look like either one of those. Maybe we have data that constantly increases and maybe increases really fast. Or maybe we have data that constantly decreases and decreases pretty quickly. In this case, we could calculate an exponential curve of best fit. Now, I know we've talked about parabolas before, we've talked about lines before, we haven't really discussed exponential curves. We will in one of our future units, but these are the three types of things we'll be looking at in our regression analysis today. So when I say regression analysis, what I'm talking about is creating a function that fits a set of data. So regression analysis is the process of estimating the relationship between variables in a data set. And when your data set appears to follow the pattern of a specific type of function, then we can calculate a regression equation or regression model for that data. And the purpose of calculating this regression equation or regression model is so that we can make predictions for values that are unknown. So when we calculate a line of best fit, that line of best fit can be called a linear regression. Or if we were to calculate a parabola of best fit, we would call it a parabola or parabolic or quadratic regression. And we created an exponential curve of best fit. We call that exponential regression. Okay? Now I can put in any data into my graphing calculator or DESMOS, and I'll show you how to do that in a little bit. And we can ask the calculator or DESMOS to create any type of regression model, but that doesn't necessarily guarantee it's good. So let me go back to my heights and shoe sizes, for instance. So I could put this data into a calculator. Now it looks linear to me. It looks pretty clear that as the values increase, so do the, as the heights increase, so do the shoe sizes. But I could ask it to create a line of best fit in any situation, right? So let's say I collected some data and the data was maybe heights and shoe sizes for men and then heights and shoe sizes for women, right? If I got one line of best fit for that data, it doesn't necessarily represent it very well. Or it's possible that you have data that's literally everywhere and you can ask your technology to calculate a regression, but that doesn't necessarily guarantee that it's good. So we need another piece to this, and we call it correlation. So when we calculate a regression model, we're also going to be able to see a correlation. So that's an actual value used to show me how close the points are to the model that we've calculated, or how accurately the model is going to make predictions. So correlation is used to determine the strength of the relationship, or how accurately the model can be used to make predictions. And to judge the correlation, we're going to look at the value of, it's either going to be r or r squared. It's going to be r when it's linear, and it's going to be r squared for nonlinear. Anything that's not linear, we'll use r squared. Okay, but r for linear. And r squared, again, r or r squared, they're really doing the same thing. It's always going to be some value from -1 to +1, where if your, let me show you this in my Scratch again. Your correlation is always going to be some value from -1 to +1, and obviously 0 is going to be in the middle of that. A +1 here would be the strongest possible positive correlation. Strongest positive correlation would be a +1. The strongest negative correlation is going to be a -1. And a positive correlation means you have values that are increasing. A negative correlation means you're going to have values that are decreasing. So if you had a correlation of a +1, that means your points are going to make an exact match to your curve. Or a correlation of -1 means your points are going to make an exact match to your decreasing values there. And what happens the farther you go from 1 or -1, the closer you get to 0, the weaker the correlation. So 0 would be no correlation at all. And then something in the middle here, like a +0.5, would be kind of a moderate. And then maybe like a 0.1 would be like a weak positive correlation. Or if you had a negative, let's say 0.2, that's a pretty weak negative correlation. So the closer you are to 1 or -1, the stronger your correlation is. Positive just being an increasing set of values, negative just being a decreasing set. And the closer you are to 0, the weaker the correlation. Okay, so closer to 0 implies a weaker correlation, which means a less accurate prediction from a model. And then closer to -1 or 1 implies a stronger correlation, which means your model is going to make more accurate predictions. Okay, so graphing calculators will do this. If you want to use your graphing calculator, you're probably going to need to Google the steps for it. But I like to use DESMOS, not only because it's free, but it's a little bit easier to see it here. And the part where we have to make the predictions is much easier in DESMOS than it is in your graphing calculator. So what you're going to do, and I'll show you the steps in a minute, but let's just write them down for now, is when you're in DESMOS, you're going to click the little plus sign that you see in the upper left-hand corner so that you can add a table of values, like the tables that we are going to go through in a minute. And then you're going to enter in your data. And then in the next line, so in the first line, you'll type in your table of values. In the next line, you're going to type in your regression model that you want to calculate, and it should be appropriate for the data. And sometimes we can go based off how the data looks, but sometimes we're going to want to look at that correlation, so we might have to do all three. Now, if we're trying to create a linear model, you have to think about what the standard form is, or typical form is for a linear function. A linear function, we're used to seeing y equals mx plus b, right? For a linear function. So we want a similar concept here. We're going to have a y, and we're going to have an mx, and we're going to have a plus b. But this isn't going to be an exact relationship. It's going to be, you know, an estimation of a relationship. And so instead of the equal sign, we're going to use this little tilde. And then when we type our information into DESMOS, it's going to relate our x's and y's. It's going to call them x1s and y1s. And so we want to make our model connect to the data. So we want to call the x's here x1 and the y's here y1. So once we type that in, it's going to give us a value for m and b so that we can actually write our model. And it's also going to tell you the correlation so you know how good that model is going to be. And again, I'll show you all this in a little bit. Okay, so linear, we're looking for y and mx plus b. For quadratic, our standard form is an ax squared plus bx plus c, and we'll look at that more in our quadratic unit, but hopefully you've seen that before. But again, we're going to have y1 here, because it'll be y1 in our table of values. We're going to use the tilde in place of the equal, and then it'll be ax1 squared, b x1, and c. Okay, and then exponential, again, I know we haven't talked about exponential, but we will. An exponential model is in the form y equals ab to the x power. So when your variable is your exponent, you have an exponential model. And then the base of the exponent kind of shows how quickly it's growing or decaying. Again, that's something we're going to talk about later, so don't worry about it too much. But here, it's going to be y1, again, to connect to this, and then a tilde, and then it'll be ab to the x sub 1 power, right, so that we connect to our data. All right, so we're going to plug in this first set of data so I can show you how this looks, and then I'll show you how to make the decision on which one of the models you're going to be using. Okay, so in DESMOS, we tap the little plus sign so that we can add in a table, and then we're going to type in our data. So 1, 5, 8, 11, 15, 20, 25 in our first column, second column, 3, 12, 15, 24, 35, 39, and 50. Okay, now notice in the, like right below the 25, right above where the X is on the keyboard, the little plus sign inside of it looks like a magnifying glass. If we hit that, it will automatically zoom to the points that we're looking at. So you can automatically see the scatter plot. And now you can see our scatter plot of points. Now to me that looks pretty linear, but sometimes our view of it is not big picture view. So it looks linear. I think the linear model is going to be good here. So let's see what happens when we calculate our linear regression. So in the next line, so notice it's our table, and then we're going to go to line number 2 here. We're going to type in y, and to get a subscript, if you just tap 1 after y, it will automatically make it a subscript. So we want y sub 1, and then we're going to go to the keyboard to get the tilde, which is in the bottom row here, tilde, and then we want m, x, and then again I need the subscript of 1. And then plus, back to my keyboard, b. And then once I give it y equals mx plus b, you can see underneath where it says stats, you have r squared and r. So r is our correlation for linear 0.99. That's pretty close to +1. That means this is a good, accurate model for this set of data. Now, would a quadratic be more accurate? I don't know. Let's see. Now, you can see on the graph there, put the line of best fit in, and those points match up pretty well. But let's type the quadratic one in here. Y sub 1, and then our tilde, and then we want ax1 squared plus bx1, and then plus, let's go back here to C. And I typed in the quadratic and it graphed at the same time. Now look at r squared as 0.98. 0.98 is not as strong as 0.99, so the linear model is going to be better. And now just to be safe, I'm going to go ahead and put in the exponential. So we're going to have y1 tilde, and then we want a b to the x1 power. And there's r squared at 0.91, which again, not as strong. So those are all actually pretty decent models. In the 90s are strong relationships there, but the best value of r that we're looking at is with our linear model. So we've decided now that this is linear. which means here, back to my paper, since this data is linear, and we can see the linear model has the strongest value of r, we're going to write our linear model as y equals, it tells us on our screen here that m is about 1.96, so 1.96 in front of x, and then plus b, and b it tells us is 1.62825, so I'm just going to call that 1.63ish, 1.63. So linear, and this was because it had the strongest r, and the r value here was 0.9922. That was the strongest value of r. That means the best correlation between that data and those points, okay? Now, you don't have to do a lot of retyping. I'm going to leave these three models in and just change my data so that I don't have to retype too many times. So I'm just going to go to the 50 and just hit delete, get rid of the data, and put the new data in. So we've got 0, 2, 3, 4, 5, 7, and 9. And then over here, 3, 8, 13, 18, 11, 4, and 1. Now I can see, let me hit my little zoom. It looks pretty parabolic to me. I don't know if that model is great, but you can see the red point really far above there, but I think that the quadratic, the fact that the data goes up and down, is going to fit the best just by looking at it. Now if I go down to my models here, we have a negative 0.2 correlation for linear, 0.756 for the quadratic, and 0.04 for the exponential. So the quadratic, again, as I predicted, is the best. So this is going to be quadratic. And that's had the strongest r squared. Remember, linear will look at r, for the rest of them we'll look at r squared. 0.756 was better than all the rest. It's closer to 1 than all the rest, or closer to, -1 if it were negative. And so we're trying to write a y equals ax squared plus bx plus c type of thing, but in our DESMOS, it gives us values for a, b, and c. So we're going to replace those a, b, and c with these specific values. So we have a negative 0.59-ish, 58-ish, just kidding, in front of x squared, plus for b, 4.76-ish. And then for c, we have 3.09-ish. Again, those are all rounded. If it doesn't tell you specifically where to round, I think the hundredths place is a pretty safe spot to do the rounding. Okay? And now we got one more go at it with number 3 here. See if I can get that to fit on the screen. Again, I'm going to not delete all my work. I'm just going to go in and delete the values in my table. And do this again. So we got 1, 2, 4, 6, 8, 9, 12. And then next column, 1, 5, 17, 70, 270. You can see these values are starting to grow pretty quickly. 504 and 4100. Hit my little zoom option. And the black one, which is the exponential model in this case, is following that line pretty nicely, right? So linear, r is 0.75, quadratic, r squared is 0.93-ish. Exponential does not just following nicely, it's following exactly. So r squared of 1 is as good as it gets, okay? So we're going to go with the exponential here. So this is exponential. And we're choosing the exponential because it has the best r squared possible, which was 1. And that means those points align exactly with that exponential curve. So exponential is y equals a b to the x, but it gives us values for a and b. So a is 1.0129. I'm just going to call that 1.01. B 1.998. I'm going to keep the extra digit there so I don't have to round up to 2, and then to the xth power. So you're just replacing the a and the b. You're leaving the x and the y in just like we did here, left x and y in, and just like we did here, left x and y in. Okay? So that's how we calculate the data. Now the purpose of this process is to make predictions, and that's what we're going to look at next. So once the regression model has been calculated, you can use it to make your predictions. If we're going to calculate an x value, then what we want to do is type the y equals whatever value we're given, y equals some number, into another line, and then we're looking for an intersection, and then vice versa. If we want to calculate a y value, then we're going to type the x equal whatever value we're given there into another line and look for an intersection. Okay, so I'll show you what that means in just a second, but we got a new set of data here. Get DESMOS going again. And I don't want to get rid of any of my information. So let me just go to my table, and I'm not sure what I did here. Somehow added a bunch of lines. Get rid of those. Okay, so go to my data, and I hit the return button instead of the delete button. Okay, so we have in this table 60 and 62, 65, 66, 59, 64, 65, 62, 60 and 61. And then in the next column, 6, 5, 7.5, 8.5, 4, 7, 8, 7.5, 5.5, and 6. Okay, let me hit my zoom. Okay, so we can see our data. We see all three models in there. Let's see, for the linear, R is about 87. Exponential, somehow these shifted, is 0.75, and quadratic is 0.75. So this is going to be linear, and that makes sense because the data, I skipped ahead a little bit, didn't read, that we have heights and shoe sizes. As I mentioned before, this is kind of a good situation where we would want to be able to use regression. We have heights and shoe sizes for a dozen women, and we saw that the linear relationship was going to dominate here. So calculating a regression model, we looked at all three options. Linear had the strongest correlation, so we're going to use linear here because not r squared, we use just r for linear, was the best, and that was 0.8669. Okay, so the model is going to be a y equals mx plus b type of thing, but m, it calculated for us at about 0.51. So 0.51 in front of x plus b, they give us as a negative 25.04-ish. Okay, so there's our model. Now, if we want to use the model to make predictions, what we're going to do is we're going to go into another line here. And somehow I got to get... Yeah, so below everything we've done, where did all my, I'm not sure what, I moved my table. Okay, whatever. So in the next line, below everything we've done, is where we're going to try to make a prediction. So it's calculated the line of best fit, and just because I can undo this in a minute, I'm going to get rid of these things we're not using just for this particular example. So we have our line of best fit. We have our data, and in the next line, what we're trying to do for part B is predict the shoe size for a woman who is 6 feet tall. So 6 foot tall woman would be pretty tall, but notice the heights in our table are in inches, but these are the x values in the situation, these are the y values. So what we're given here is an x value of 6 feet would be 72 inches tall, and they're saying predict the shoe size. That means tell me the y value when the x value is 72. So in the next line, I'm going to type in x equals 72, and it's going to put a vertical line into my picture here. And I'm looking for where that vertical line intersects my line of best fit. And that intersection tells me that when you have a height of 72, your shoe size is going to be about 11.353. Now, this takes the context out. Obviously, we can't have a shoe size at 11.353, but from this intersection, we could say that if you're 72 inches tall, you're probably going to wear like a size 11 or a size 11.5, okay? So here we see an intersection at 72 and 11.353. So that means we're looking at about, and get rid of this, 11 or 11.5 shoe. Okay, and then we do the same thing for part C. It says predict the height this time. This time we're looking for an X value for a woman who wears a size 9 shoe. That's telling me that the Y value is 9. So back into DESMOS, and I want to get rid of this time. I got rid of the X. Now I want to know what's happening when Y is equal to 9. So if I type Y equals 9 in there, it gives me a horizontal line. And I'm looking for where does that horizontal line hit the line of best fit. So that intersection says that if you're wearing a size 9 shoe, you're probably about 67 inches tall. So the intersection at 67.345 and 9 means you're probably about 67 inches tall, which would be 5 foot 7 inches. Okay, all right, we got one more to work on here. So we have some years data showing the number of sell goods in billions exported from the United States. So we have a year where goods were exported and how many millions of goods were exported in that year. And I put here, let X be the number of years after 1998. When we're calculating regression models dealing with time, we should always be starting at time 0. So 1998 would be 0 years after 1998. This would be 3 years later, 4 years later, 5 years later, 6 years later, 7 years later, 8 years later, 9 years later. So we don't want to type in 1998, 2001, 2002, and etc. It's going to skew the y-intercept if this happens to be linear, or really y-intercept for any set of data. But anytime we're using time, you want to start at time 0. So if 1998 is time 0, 2001 is 3 years later, and so on. So we're going to enter the 0, 3, 4, 5, 6, 7, 8, and 9 for our x values. Okay. Now, didn't really want to swing that all the way over there. I have to undo some of my damage here. So I'm going to hit my undo button and see if I can get back my models that I deleted out, because I don't want to have to retype all that. All right, so that's all back in. Now I need to fix my table, make it correspond with what I have in my new problem. And okay, so we have time 0, 3 years later, 4, 5, 6, 7, 8, and 9 years later. And then here, 231.1 and 201.3 and 151.4, 147.9, 133.9, 127.4, 121.5, and lastly 118.7. Okay, so I'm going to go back, look at each of my models. Quadratic, r squared is 93.93, exponential 0.9304, so quadratic is slightly better than exponential. And then linear, not as good. Oh, actually, linear is negative 0.94, so it's a negative correlation instead of a positive, but 0.9495-ish is going to be better than the 0.93 that we have in the others. So we're going to go linear again here. So I'm going to get rid of these two. So again, this is going to be linear. Had the strongest correlation, which was r being negative 0.9491. Okay, so y is going to equal m is negative 13.27 in front of x, plus b, which is 223.84-ish. Okay, let me just go back to my data. I'm going to hit the plus sign there so I can see that the line looks pretty good there. Okay, now part B says predict the number of goods exported in 2013. So the years, these were x's, the number of goods, these were y's. So predict the number of goods exported, that means predict a y value in 2013. Now 2013 would be 15 years after 1998, so this is telling us that x is 15. So I'm going to go into my next line here, type in x equals 15 and look for the intersection, and that's going to be over here. So we have this intersection at 15 and 24.729, so that tells me in 15 years there's going to be about 24.7 billion goods exported, right? About 24.7 billion goods. Okay, and then lastly, if we want to predict the number of exported, predict when, that means predict an x value in this case, the number of exported goods is going to decrease to 50 billion. That's telling us y is 50. Let's go here, get rid of the x equals 15, put in y equals 50, and look for that intersection. So 13.096 comma 50 tells us that when we have 50 billion goods being exported, that it's probably 13 years. So this is about 13 years after 1998, which would be in the year, what, 2011, according to this data. Okay, and there it is. So you're going to be predicting different models. You want all three of the models in there at the start to see which one has the strongest correlation. And then once you have the model established, you're going to be typing in values of x or values of y to make predictions based on that model and based on that data. Okay, so that's it for today. As always, if you run into any trouble, let me know via email. Good luck with the practice. I put pretty detailed solutions